So, Professor Michael Corti, I understand that your research focuses on the use of gold nanoparticles in a medical context. Tell me what that means.
Well, for thousands of years, people have known that gold is one of the very few elements that doesn't corrode. And people have even drunk gold potion in time. In the last 10 years, people have realized that gold could be used to make a kind of nanoparticle that could target or diagnose disease in people. So we've been engaged in that topic at UTS as well since about 2005, and it's a really exciting topic.
And what is a gold nanoparticle?
Well, what it is, it's a tiny piece of gold that is so small that it's more or less invisible to normal light, and it's made up of not squillions of atoms, but merely thousands of atoms. It's so little that it can float around in water or in the blood, and it doesn't settle out.
And how might this help with the treatment of disease?
The beautiful thing about it is that we can stick other molecules on the surface of the gold in a very controlled way. So a chemist, for example, can stick on an antibody to some disease, for example, or to a different kind of cell. We can stick it on the gold particle, and then we can inject that gold particle into a biological environment, and it will stick on the target. And once it's stuck there, there's a couple of interesting things we can do. One of those things is we can get a color change and make a diagnosis. But actually at UTS we've gone the next step. We want to actually attack disease. So once we've got our gold particle to stick on the target cell or target organism, then we use it like a tiny nano antenna, like a little radio antenna, and we zap it with laser light of the frequency that's tuned to that gold particle. Laser comes in, zaps the gold particle, particle gets hot, kills the target, whatever it is. So it's pretty selective, and that's the beauty of it. That's why it's a golden bullet. People always spoke about, silver bullets for medicine, some kind of treatment that only goes to the disease and leaves the rest of us untouched. So this is what happens here. It only goes to the thing it was targeted to.
So just explain how that works. How do you make your particle only stick to your target?
Well, that's the magic of the immunology and the chemistry. You have to find an antibody that will stick to whatever it is you want to target. If it's a kind of cancer, you have to seek an antibody just to that one kind of cancer. That's the thing you extract, and then using chemistry, you attach it to the gold particle. Now, the antibody works like a sort of a gripper thing, but it only grips on its target, so the gold particle will only stick to the target. And actually, this is the expensive part of the whole business. The gold is nothing. The antibody is really expensive.
And what kind of diseases are you focusing on specifically?
So we are looking at treating infectious diseases at this time. So we're not looking at treating cancer because that's not really a strength around UTS, but infectious diseases, that is something that UTS knows about, and that's why our research is targeted at infectious diseases.
And what kind of results are you getting?
What we have found in a fairly extended and rigorous series of trials is that we can target gold particles to live Toxoplasmosis gondii infections and selectively kill them in blood. And that's very encouraging and exciting because if you can do it with toxo, in principle you could do any other infectious protozoan disease, and that includes malaria, for example. The other thing we figured out, and that was somewhat accidental, is we can also target certain kinds of autoimmune diseases. So this is early days, but you can target the body's own immune system and target its macrophages, its white blood cells, and this opens the door to a whole lot of other things, including, for example, some conditions associated with obesity or perhaps arthritis. All of these diseases are actually associated, they're linked, they've got a lot of stuff in common. So maybe there's a pathway here for the future.
Is this something that we should be getting excited about?
Well, we're really excited. But in all of these medical things, it's really important to know it takes years and years and years of trials before it reaches the public. It can be like 20 years because everybody plods through rigorously and systematically. They've got to prove that it works. They've got to prove that there's no bad side effects. All of that. It takes ages before these inventions see the light of day. And we're in the early stages of this, but we're excited, yeah.
Well, Professor, even though it sounds like it's a while away, to me it sounds like developing treatments with very little side effects is very exciting. Thank you so much and good luck with your research.
Thank you.